Hello and welcome everyone. Thank you Dan and Vlad for the introduction and the chance to talk there. I'm going to be talking about faster problem solving with pandas. So as we were discussing in that intro, not focusing on getting the latest cutting edge machine learning techniques or really any machine learning at all, but doing one stage back, that slightly earlier piece where we have to do our data manipulation, fetching our data, munging it, doing something to make it useful for us. I've been in the field for a long time. I'll introduce that in a second. And I keep seeing these issues turning up where people prototype solutions on smaller data sets. It works just fine in Python with pandas. Then they go to their true production data set with a much larger volume of data. And all of a sudden they have problems. They can't fit their data into RAM, and then they break. They just stop there. What do I do now if I can't fit it into RAM? So we're going to look at some ways of compressing our data down. What if my code is too slow? I've written some applied functions and it's just really slow. Well, we can vectorize. We'll talk about that. I do my GroupBys, and my GroupBys are slow, or they feel chunky, or I can't really understand what's in my GroupBy. I don't have a good mental model. We'll talk a bit about that, debugging in particular, and a third-party project on Pandas that helps our GroupBys to go faster, which is known by almost nobody at the moment. We'll also look at using Numba, the just-in-time compiler, to compile rolling functions and talk about where Numba can be used to enhance the speed of pandas in general. Not many places is the answer, but it's increasingly being integrated. And I'll give you a couple of optional dependencies that are mentioned on the installation page. The installation page says, almost jokingly, you should install these things. Pandas will go faster, but they're not installed by default. So they're easy wins for you, and I'll give those a bit later in the talk. I'm also including a cheat sheet for you that comes from my course on high performance Python. I'll give you the link for that later on. So introductions, I'm an interim chief data scientist. So I run my own company. I go into firms that have problems delivering their solutions, and I help teams to get better at delivering their solutions. So particularly I will coach a team looking at projects, de-risk them, get rid of some projects that just aren't delivering for whatever reason, and help the team to move forwards in delivering solutions. I've spent 20 years building solutions for clients. Now I help teams to work harder at delivering things that work and bring value and joy to the clients internally. So I've been doing this for 20 or so years, working with a bunch of big names, particularly in the UK. I'm based in London, so I often work with London-based firms, but sometimes internationally, certainly throughout Europe. I also give lots of public talks and conference talks, keynote talks. Part of that is because I'm a co-founder for the PyDataLondon group. So PyData is a meetup group of 180 meetups around the world for Pythonic data scientists. So PyData, the pragmatic business use of Python in data science. We've got the largest in London, 7 years old, 11,000 members. If you're ever in London, and when we're past the pandemic, if you'd like to join us, I would love to have you along. Alongside building these communities and giving these talks, I also run training courses. One of my training courses is Higher Performance Python. That's based in part off of me writing a book on high performance Python with O'Reilly. That's the second edition, which was published last April, which includes a section on pandas and more. In my training course, I go further than that, even as far as using DAS to scale up our data sets to bigger than RAM problem sets. So some of that material from my training course is included here, including the cheat sheet that I'm going to give you later on in the talk. So in this talk, we're going to be looking at a lot of benchmarks. These benchmarks are specific to my machine. Typically, I work on Linux. I've got an i7 4-core, 4-hyper-thread laptop with 32 gigs of RAM. That's where these benchmarks come from with the current version of Pandas. All benchmarks are wrong, we know that. So whenever you do your own benchmarks, things will change. One thing that particularly will change things is if you've got different data, and of course you've got different data, it'll look different to the data that I've got here. Then with different data, your numbers will vary. So don't worry if your numbers are different. Worry about benchmarking. Always measure your results and check that things are working for your specific data set. So don't just take my advice, you've got to think about your data set. And I'll give you some timing tips in this talk. So for those of you that aren't familiar with Pandas, I'm imagining most of you in this talk have come across Pandas. It's super popular. It is one of the bedrock tools for data analysis in the Python ecosystem. Often we use Pandas to prepare our data before we do reporting, data manipulation, statistics, or putting it into scikit-learn or TensorFlow or the other machine learning frameworks. So Pandas is everywhere. Pandas has evolved It's about 12 years old. I think it's 12 years old. It's evolved heavily in that time. It's had a very organic growth behind it, which means that there's lots of warps in there. So some things you do one way and it's slow. You can do things another way. There are many ways to solve the same problem, and you can get speed ups or RAM savings. It's always evolving as well. It's super active. Some of the developers are shown on the right hand side there, and it's forked heavily. It's a brilliant project. It's improving its engineering on the inside, but it's always evolving, so it's kind of hard to keep up with it. So we'll cover some of the new things in this talk. Operations can be RAM expensive. One of the tips is always to have 5 times spare RAM from your data sets. If you have 1 gig of RAM, you want another 5 gigabytes, potentially for some of the intermediate stages of some complex operations. That's really expensive, and we don't spill over to disk. So if you run out of RAM, that's it, you stop your analysis, unless you switch to an alternative technology like Dask or Vakes, which we're not talking about in this talk. So compressing and using less RAM is important, and we'll cover that. Super wide, super rich API, particularly for time series tooling, which takes you beyond what you can do in SQL very quickly. One point to mention that, and Dan and Vlad made this point, the speakers here are volunteering. I'm certainly a volunteer. I run my own company, so I'm here off my own back. The people who write these open source tools are also volunteers. So remember to say thank you. As and when we're back at a physical conference and you meet some of the core developers in a project like Pandas or Matplotlib or NumPy, go and say thank you to them. Say thank you to your organizers at the conference. Say thank you to your speakers at a conference. It makes the world a better place. So I'm going to use one data set for most of this talk. This is the UK land registry data set, so 25 million rows for roughly 1 million house purchases per year for 20 years. So it's 25 million house purchases stretching back over time, and you can see a snippet of the data there. That's the head of the data frame. You can see on the left-hand side, I've got an integer price, I've got a date, which is a date time, I've got a bunch of string fields, so postcodes, PT there, that's property type, flats or detached houses, so apartments or single dwelling houses, and a bunch of other details. There's lots of text. Pandas supports text, but it's not brilliant at the memory side of holding on to text. So actually that's 4 gigabytes on disk, and it's about 20 plus gigabytes when it's in RAM. Yeah, 20 gigabytes I can see there. So actually it's huge when it's in RAM. It expands massively, and then on my 32 gig machine, all of a sudden I'm running out of space to do intermediate operations. So this is an open source data set. If you want to mess around with house prices and their evolution over time, I recommend you go and get this data set from that GovUK link down there. So we load in this data set. We look at our machine system monitor and it says you're running out of RAM. What do we do? Well, the first thing we can do is to use info. So on the left hand side, I've got df.info. That tells me about the columns in my data set and their data types and how many rows I've got. So I've got 25 million items there and I've got 16 columns. Down at the bottom left hand corner, you can see highlighted in red 3.1 plus gigabytes. That plus means it's an underestimate. Actually, it's a really big underestimate. df.info does not query the true size of every string entry. It doesn't query the size of any string entries. And when you've got lots of string data, it just means it's guessing at the low end. If on the right hand side, you see the top right corner, the red highlight around memory usage equals deep. Now, Pandas will introspect every single item, particularly string. It's every single object item, which are often strings. It will ask every single item, how big are you? How many bytes for your entry in this row? And so how many bytes for every entry in every column in every row for all of those strings? And all of a sudden, our memory usage is reported as 21 gigabytes without a plus, no longer an estimate. This is the true measure. So all of a sudden, we get the idea that we're using 2/3 of the RAM on my laptop, and then that leaves very little RAM for other operations. So you can ask yourself as a simple set of tips, do I need all of this data? Do I need all of those columns? If I'm doing price and date analysis, I probably don't need the address details. Maybe for some geographic work, I want one of the high-level geographic addresses like a city or a county, but I probably don't need to know the actual street number for those houses. So could we drop some of the columns and get rid of those expensive string data types, or could we subsample our data? So rather than using 25 million rows across the 20 or so years, instead maybe can we just subsample and take 1% of the data to have a fast, easy analysis if we want all of those columns? Because if we've got less data, all of our operations go faster. And a research flow, that's really important. It doesn't help you at production time if you need to process all that data, but it does get you past the early stages of your research. So here's the slice that we're going to use. I'm going to use all 25 million rows, but only 4 columns. So I'm going to take from the data frame county, and you can see some examples in the head below. So county, that's a region in the UK. PT, that's property type. So F is a flat, an apartment. D is a detached house, so it's a single house that's separate, it's got all of its own walls. And then there's semi-detached and others, so houses that are joined together and terraced. Date, that's the date going back to 1995, and price, and the integer price. Now, if I take that subset, so that's df few cols rather than df the original raw data set, and I do memory usage equals deep, we see that although I've gone down to 4 from approximately 12 columns, I haven't shrunk the RAM by down to 1/3. I've shrunk it much more than that, from 20 gigs down to 3.4 gigs. And that's because we've removed a lot of the string columns, and those are the ones that are really expensive here. So now let's think about how do we compress some of this data as one of our options for making our analysis code go fast. So here I'm going to use the categorical data type. This was introduced a couple of years ago. It's a way of compressing the in-memory representation without changing how you manipulate your code. So your code looks the same, you get all the same operations, but behind the scenes you've changed how these columns are represented in memory. So you can see on the top little code snippet there, I'm making 4 new columns in a df slimmer cols. So that's a new data frame. County cat, I just put underscore cat. That's my way of knowing that I've changed the type. So county underscore cat is the as type category you can see on the right hand side. So I'm taking county, which is a string data type, the object field, and I'm using as type to change its type to a category. I do that for 3 of them, the property type and the date. And then with the price column, which is by default an int64, so that's an 8-byte entry per row, I'm turning it into an int32, which is 4 bytes. If my numbers aren't super large, my prices are not super large, I can go from a 64-bit representation to a 32-bit or possibly a 16-bit representation and save bytes. If you've got thousands of columns in int64, float64 form, and you can cut them down to half their size or even a quarter of their size, you can save a lot of RAM. So that's a nice little tip. You can use as type there to change your numeric columns to a smaller byte representation, or change your string columns and date columns to the categorical. Bottom left corner, I look at df slimmercols.info with memory usage equals true, and I find out now that I've got memory usage of 200 megabytes. So 200 megabytes if I go back from 3.4 gigabytes, another 10 times saving. That's a huge saving in RAM. I could do that on the original data set and I get that same huge saving. Not only do we save RAM, also some of our operations will go faster. There's an important point. I did these conversions on 3 columns, 2 of them were strings and 1 of them is a date column. You can do categoricals for any column type. It doesn't matter what the column type is, you can do it for any of the column types. So if you've got, say, a spreadsheet full of the same date in one column, which is the date that spreadsheet was produced, here's a trivial way to compress the memory usage of all of those date times to the cost of 1 datetime object. We want to check that we're not losing any data whilst we do all of this. So we should check during our conversions that nothing is lost. This is another tip for you. Here I'm saying assert, that's a Python assertion, assert that for all items in df slimmercols on the price I32, so that's the 4-byte column that I've made, all items are equivalent to the original items in the int64 price column. So that's assert, I do the comparison, I've got a dot all on the end there because with 25 million rows, I get 25 million Boolean results and I want all of them to be true. Otherwise, I have to show an error message there. Personally, when developing code inside, certainly with Pandas, but any research code in scripts or in notebooks, I litter my code with these kind of assertion statements. This way, I'm encoding my assumptions at research time into the code as I manipulate my data, change it and improve it, so that when I get the new data set tomorrow, and I've forgotten the assumptions that I had by tomorrow's development, and I run it through my code, these assertions blow up exactly when they should blow up. This here, if we had a new price that required an 8-byte representation rather than 4-byte, that would give us a rounding error in our data set, which if we didn't have an assertion would propagate into our later analysis. Here I would catch that problem at the point where it occurs, rather than causing me to do an expensive debug operation later on, trying to figure out why the heck I've got some strange results in my data. So another tip for you, always put these assert statements in, or raise an exception if some logic doesn't match your requirement. Certainly you don't want to use asserts in your production code, you want to raise exceptions based around some logic, but this is a super cheap and easy way to check that your assumptions are encoded as you're developing. So now we've got our categories here for our 2 strings, our date and our price field I've encoded as an int32. Now that saved our RAM, great, we've got a 10x saving in RAM, that's brilliant, I can get more data into RAM. And I can do more complex operations because I've got more free RAM. What about doing an operation? So in this case, bottom left corner, df few cols. This is the unencoded version. I'm going to take property type, that's the .pt column, and I'm going to do a value count. So I get a value count telling me how many different property types I get. This costs 2 seconds. So it's kind of slow on 25 million rows because it's looking at strings and it has to go and ask everyone this simple operation, but do it 25 million times on strings. On the right hand side, I'm using %time again on df slimmer cols. So that's the data frame where we've converted our types. I'm talking to pt_cat, that's the categorical variant of pt. I didn't have to change the name to put _cat there, that's just for my debugging and communication to you. I asked ptcat to do a value count, and I mentioned before that when we do a categorical encoding, we get all the same operations. It doesn't change how we deal with our data. So effectively that categorical encoding is hidden in the background. We'll dig into it in just a second, but it's hidden in the background so you can do your regular operations. You do a value count, we get the same result out, but we don't get it in 2 seconds, we get it in 0.1 second. So that's what a 15 times speed up there. That's a huge speed up for some of these common operations just for encoding your data as categoricals. You may be asking now, well, what's going on inside this categorical data type? Well, if we ask df_slimmercols.ptcat to look into the .cat accessor, remember that if you've got strings, you can do .str to get all the string operations. If you've got date times, you can do .dt to get to your date time operations. And with a categorically encoded column, you can do .cat to get into the underlying categories. You wouldn't normally do this. You don't really care about these technical details, but it's good to have it in your mental model. So I can say .cat.categories, and we can see that there are 5 categories dfost. Those are the original strings. They're represented once, not 25 million times. In .cat.codes, we have an integer representation 0, 1, 2, 3, 4, which will encode those 5 items that we're looking at. This means we only have to store int8, so tiny 1-byte integers, because we've only got 5 numbers to count. We store internally 25 million int8 items, which are the lookups back to the underlying categories, and that will happen seamlessly behind the scenes. So here I'm looking at the tail of ptcat.cat.codes, and then I can see that there's 03400, and you can see those mapping on the bottom right hand corner of the df_slimmercols.tail. So we didn't have to change anything in our categorical columns and how we manipulate it. We just do a tail and we get the original strings back there. Those categoricals are hidden behind the scenes. So they're free and they're easy. They save us RAM and they make some of our operations go faster. They're pretty cool. You should give them a go. I mentioned that you can do this on date times as well. So here at the top, for example, I'm getting my date cat and then I'm calling .year and I get the year out from that date time field. I didn't have to do anything to deal with the categorical type. All those operations are passed through. So if you've got lots of repeated dates or strings, categoricals are brilliant. Definitely think about using them if you've got these repeated instances on large data frames. It really can have a big impact. You may be curious, what kind of results do we see in this data? So here's one screenshot. Here I have done a GroupBy on my data, breaking out the number of sales that we see, so the size of the GroupBy, grouped by year and grouped by property type. So we had 5 property types in 25 years. We can see the volume of sales rising from 1995 in the UK all the way up to 2005, 2006, 2007. Then we get the Great Recession for a couple of years. All the sales drop off. This was the Great Recession 12 years ago, a very terrifying time. Sales are flat for a couple of years and then they begin to pick up again. And of course, in the most recent years, the numbers are very low because of underreporting. So it's not the case that sales have dropped off to zero in the UK. It's just that we've underreported and not codified these in the open source data set. But it's always nice to kind of visualize this kind of thing and realize that actually my latest data is not up to date. One of the ways of being performant is drawing lots of diagrams and analyzing our data. So if you're not yet drawing many diagrams in your work and you're not customizing your diagrams, top tip, go and make lots of diagrams. It's much easier to understand your data if you've drawn it. So we've done our GroupBy there. Was it quick enough? Well, yeah, maybe that GroupBy was quick enough, certainly quick enough to demonstrate one easy result. What about if we want to do some custom functions? So let's say I'm doing a GroupBy and I want to run an applied function. So I want to use apply on my own custom function. Here I've got a trivial function. It's very silly, but it demonstrates the point. Count large will count the number of sales that are above £500,000. And it will take the size of that series, divide them through, we get a percentage. So we can see per property type what the percentage of sales, or in this case, it'll be by county, so by location. Per location, how many sales are above a threshold and below a threshold. We could do this other ways, of course, but this way just demonstrates a one-liner for a custom function. And then if we take that function, we do on the second cell, dfucals group by county, so group by locations, take the price column and apply our function. We then get some results. We sort them, sort values, ascending force. Then I'm going to apply a lambda function. You may not have seen this. I'm going to apply this, which will then give us a pretty printing function. So I'm going to apply lambda s. F, that means I've got a format string and then squiggly brackets. I'm going to take the string s and times it by 100. And then I want 0.1, so 1 decimal place with a percent afterwards. And that gives us that nice pretty printed result down below. That takes 5 seconds, 4.77 seconds. That's actually pretty slow. That feels like a really fast operation, but it's going really slow here. Can we do better? Tip for you there, using percent time as your timing profiling operation means you can have multiple lines of code in a cell, whereas percent time lets you just have one line of code in a cell. So percent time will record the wall time, how long the operation took overall, which is great for easy debugging. So we had our applied function a moment ago, and it was really slow. What could we do to make this faster? There's a couple of things we can do. The obvious solution is to come up with a vectorized approach. Vectorized operations happen at the C level or the Fortran level behind the scenes, not at the higher level Python interface, which incurs quite a lot of overhead. Here I'm going to make a copy of my data, dfucals copy. I'm going to make a new column, price large. This new column is a Boolean indicator. So I take dfucals copy dot price greater than 500,000, make 25 million trues and falses. Are they above or below the threshold? Then I do a group by. This is going to be an intermediate operation. I do a group by on county, taking price large, and I'm going to ask for 2 aggregates, one on sum and one on size. This means I know how many were true and I know how many were in that group. And you can imagine we can divide these through in a minute to get our percentages back. If we're going to time this in a moment, we have to remember that we're not timing just the cost of the group by, but also the cost of generating that intermediate result, that price large. Otherwise, we'd not be timing the complete operation and not doing a fair comparison. So here's the vectorized pre-calculated version. We're doing percent time on the whole cell. I've got my copied data. I create the price large field in the first line. In the second line, we do the group by, aggregating by sum and size. In the third line, I break out sum and size and divide them through. Now I get the percentage back. And the fourth line is the same pretty printing that we saw before. We get the same results out 3.3 seconds, so 1.5 times faster. One thing I've noted by going down this route is that the cost of the operation changes dramatically by the number of groups and the number of things in the group. And it just depends on the different data sets. So this is something you should bear in mind. The downside of this is we have to make an intermediate column. And of course, that costs some more RAM. If you would have to make many columns to vectorize your solution, it might go faster, but cost you a lot of RAM, and that might be the right trade-off if you've got enough RAM. I always recommend the easiest way to make developers more productive, double the RAM in their machines. Just give them more RAM, stop them thinking about the optimizations. But do bear in mind that if we vectorize, we use intermediate RAM representations, that costs some RAM, but we do get a speed up. And this is going to vary depending on your data set, but almost certainly going down the vectorized route will give you a faster solution. But your code's perhaps not as easy to read and so perhaps not as easy to maintain. Maybe there's a development efficiency trade-off there across your team to bear in mind. Now, what's happening inside those group buys? So we can dig into those group buys. We can do things like take my group buy on county, price large. That gives me a group by GPBY object. I can say group by.ingroups, 128 items. So I've got 128 groups in there. And I can print out the keys for the first 10. It's a dictionary-like object. So I can see the keys that are in there. That means then that I can go into the groups and I can give it the string of one of the groups, Bath and North East Somerset, and I can get the int64 index. That int64 index is the same index that we have on the 25 million rows of our data frame. So row 5628 will have one of the Bath and Northeast items, and we see that in the bottom cell. If I go to the groups, I get the 0th item, that's 5628, and I dereference DFU calls with a .lock on that item, and I get one of those series objects back representing that row of data. So this is a nice, easy way to dive into some of this if you don't have a good mental model of what's happening in your group by. It's well worth diving in. You can do a dir on your group by. That will give you a directory of all of the functions and attributes inside your object. Everything in Python's an object. So we do this on group by, and you'll see a couple of hundred results. And if you scan through those, you'll see things like get group, groups, head and history already know, and a bunch of other common items. Go in there, play, read the docs, see what's going on inside that group by, pull it apart and improve your mental model. So let's move on to some time series work. So one of the lesser known operations in Pandas is rolling, so time window based rolling operations. We can take a time series, take a window on it and slide that window over time, doing the same operation multiple times across that moving window. That's really slow, but it's a good way to get summarized versions of what's happening in some period of time. Here we're going to look at analyzing the number of sales in a window of time, a number of days, and how that varies. So we get this rolling window. You can choose different windows, 1 week, 10 minutes, whatever. User-defined functions were traditionally really, really slow. So your provided pre-built functions in Pandas were super fast. They were written in C or Fortran. Anything you provided went really slow. Numba is a just-in-time compiler, so that means it compiles up your code, your custom function on the fly. Numba support into the rolling and expanding window operations was added in the last year or so, and it gives us a really good speed up. So we can get faster operations. Here's an example from the documentation. If I make data a series with 1 million items in it, I make roll, which is a sliding window, 10 items at a time, and I apply a function f on it. If I do in the second cell, time it with roll.apply, function f on our data, with engine Python, the traditional engines will compile to C in the background, guessing the types as best it can. That operation takes 5 seconds, kind of slow. On the second cell, I compile the same thing, but with engine equals number, and it goes faster, 0.9 seconds. That's brilliant. Number's a just-in-time compiler. The first time we compile, everything goes slow because we have to compile. The second and subsequent times, we have the compiled function cached. That's the bottom cell. Now the same operation takes 0.1 seconds, and it'll take 0.1 seconds every other time. So that's a huge speed up. So experimenting with engine equals number, if you're doing rolling and expanding window functions, could be a really interesting idea. We can do the same thing on our data. Here I'm going to make a conservative estimate function. This is a bad statistical function. Don't do this on your own data. This was me making up something that required a little bit of logic just to demonstrate the idea. So I've made a conservative estimate function. We're going to look at a sliding window of several days on our data, and then we're going to take either the median price or the minimum price, depending on how many items are being how many houses have been sold in this sliding window. And it's a several-day window, so at weekends, few properties are sold because the lawyers' offices are shut. They're not doing any paperwork. And so the count goes down during the week, the count goes up, and we can take a different estimate of price. At the bottom, I'm setting the index of date, I'm querying only recent items, and then I give us a little head and we can see some of the data there. What really matters is, here at the top, I do my 400,000 sample of data with a rolling window of 3 days. I do a regular apply of my function, so that's the regular Python version, 2 minutes. On the bottom right corner, same thing, engine equals number. This is the second run, not the first, so we get rid of the compilation overhead. 37 seconds, so 4 times speed up just by changing the engine. If you didn't know that number was integrated there, now you do. You should go and experiment with this. Numba doesn't know much about Pandas yet. Numba's being integrated. Numba knows all about NumPy, the underlying numerical Python library. Pandas uses NumPy and extends it and adds its own data types. Pandas doesn't know about these extended data types or a lot of the machinery inside Pandas. So you can't just use Numba wherever you want as an accelerator. But if you know that you can jump down behind the scenes, then you do get a nice speed up. Wouldn't it be nice if we could do a GroupBy? So not an expanding or rolling window, but a GroupBy, and take that apply and compile that apply? Well, we can't, not yet. There's an open pull request. It's been open since February 2020 with lots of discussion, but there's no solution in there yet. If you want to make the world a better place, you could go and contribute to that pull request. That'd be brilliant. I'd be super happy if you could go and do that, because that would help make my life more interesting and faster. And I'd include that in my book and my courses. I'd love it. It'd be brilliant. But right now we can't do it. So what if there's another solution? There's a third-party library that I've been itching to try for a while called numpy-groupies. It's got about 30 stars on GitHub. Almost nobody knows about it. There's very little contribution, but the code's nice, it's clean, and it works. We can do a faster GroupBy than what's available inside Pandas. We jump through a couple of tiny hoops. On the bottom left-hand corner, I'm doing the GroupBy on a key. This is a new column that I made up, is new, a Boolean indicator of whether the property is new or old. And then my ag call, I think, is the price in this case. So I want to group by whether the properties are new or old, take the price, calculate the mean. If a property is old, the price is lower than if the property is new. It seems reasonable. That's in Pandas. That takes 0.6 seconds, which is pretty fast, right? That's doing all of the aggregation and then doing the operation on the aggregation. That's fast. On the right-hand side, I'm taking the Pandas factorize method, which will identify the different groups, the 2 different groups in this case. So for every one of the 25 million rows, whether you are in group 0 or group 1, or the many groups, the 5 groups, if we were dealing with those, the property types we looked at earlier. So we have to do that. That factorize operation's quite slow, actually. Here it takes about 0.3 seconds out of that cell's execution time. Then we do MPG, that's numpy-groupies aggregate, giving it that group index, we're giving it all those groups, giving it the column that we want to aggregate against, that's the price column, and asking it to calculate the mean, and the whole result takes 0.4 seconds. This is on the second run. This is because the mean function has been compiled by Numba inside numpy-groupies in the background. All of the speed up comes because Numba is being used in the background. So we can go faster on the aggregate, and the factorize method is fast, but not super fast. I've just been experimenting last night with a faster version of factorize that's data type specific, and I'm going to contribute that back to this project. If you use numpy-groupies, I would love to hear about it. Contact me on Twitter and say that you've used it, or even better, put in a pull request to that project. It's underloved and needs more attention. Also bear in mind that if you start doing things like unpacking some of your data, thinking, I know, I'll just make my code faster, you might have unintended side effects. You always have to profile. That's one of the clear tips out of this talk, always profile. On the left-hand side, I'm doing % time on exactly the same cell we had before. Group by on a key, take an ag call and do a mean. Takes 0.6 seconds. On the right-hand side, I'm doing the same group by, the same aggregation. I'm just doing it on df, dereferenced by my key and ag call. I've only got 2 columns rather than multiple columns. Hey, that feels like there's less data being referenced. Maybe things go faster. No, it takes 0.7 seconds. It's even slower. It turns out this makes a temporary copy of the data, and then it applies the aggregation. That temporary copy takes time, and that's why we get this increase in time. Whenever you think, I know, I'll just make a little change to my code and it will go faster, always time it. The number of times I've intuitively thought I'd make something better and I've made it worse is ridiculous. I've just learned always time it. Here's a couple of free libraries. We're just getting to the last bits now. We're going to wrap up in a couple of slides. Here's a couple of libraries that you need to install. These do not come installed by default. At the bottom is the documentation on the Pandas installation page. It says, hey, numexpr and bottleneck will make your operations go faster, but they're not installed by default. So the easy tip is pip install numexpr and bottleneck or conda install, and then your operations will go faster. Here's an example. If I take, so here I've got bottleneck installed and I'm going to disable it for the purpose of a benchmark. Here I'm taking the original price and int64 column, turning it into a price f64, a float 64 equivalent, and using some asserts to check that I haven't lost any data. Very important, of course. In the second cell, I'm using pd.options, so pandas options, in the compute option set to turn off the use of bottleneck. So bottleneck was installed, but I'm deliberately disabling it. I do a mean operation on my price as a float 64, takes 0.1 seconds. Well, that's pretty fast. If I turn the use of bottleneck back on, the same operation takes 0.05 milliseconds. So it's 3 times faster. 3 times faster for some of our operations just by installing a library which has no downsides. Just install bottleneck and numexpr, and then your life will be better. You don't have to import it. You don't have to mess around with the PD options. You just make sure you've installed it. Just pip install bottleneck, and your pandas operations will run faster, or the same speed. There'll be no downside. If you want to go even faster, you can drop down behind the scenes, behind the back of pandas. In the second cell, I'm taking my price f64. I'm saying to numpy, give me the underlying numpy representation. And then when I call .mean, I'm calling numpy's mean, not the pandas mean, and things can go faster again. There's some caveats around this, which I explored in my PyData Amsterdam 2020 talk. That's on my blog at ianozsvald.com if you want to go and dig some more. Just know that if you drop down to numpy, typically you can call the numpy operations and get another speed up. Right, I've got a cheat sheet that comes out of my class. I'm making it available for free. This link will be on the next couple of slides. bit.ly hpp_cheat sheet. There's no sign up, just get that, you get a PDF, and it contains about 5 pages of notes from my high performance Python class. You're welcome to take it, and if you've got questions, tweet back at me. If you want to read some more about writing better pandas, so using a smaller subset of pandas, because pandas has many ways to solve the same task, I really like Ted Petru's Minimally Sufficient Pandas article. He talks about all the different ways you can solve a problem in pandas and how having a restricted API means your team has less to understand to achieve the same result. I think that's a neat idea. So Google for Minimally Sufficient Pandas and take those tips. So let's wrap up. Remember to go to categoricals to get speed ups and to save RAM. Cut your data types down from int64s and float 64s with 8 bytes down to int32s and float 32s with 4 bytes. It's half the size. Sometimes the operations will be faster. They shouldn't be any slower, but they will take half the memory. Always install bottleneck and numexpr. Every time I do any experiments, I import bottleneck and discover, no, it hasn't been installed. I have to go and install it again. It's a bit annoying. Just remember to install those 2 libraries. And then go and read the new documentation, because that's where you discover that Numba is being increasingly integrated, which makes things faster. So pandas have lots of new options. You should go and read the documentation. Some of this is covered in my book, High Performance Python. That's the 2nd edition. I put out a newsletter every 2 weeks. It's on my blog under the Data Science Jobs tab, because it started as a jobs list based out of jobs in London. Now it contains my tips and some jobs as well. You're super welcome to sign up. If you go to that link, ianozsvald.com, Data Science Jobs, on my blog, you can look at all of the old articles, all of the old newsletters there, and decide if you want to join up. Over my shoulder, you can see postcards on the wall. I love receiving postcards. If I've taught you anything interesting, please send me a postcard. Send me an email. I'll send you my address. It will go on the postcards that are all around my office. I love receiving postcards. Go to bit.ly, HPP cheat sheet, and get my cheat sheet. And I'm happy to answer questions on Twitter and inside the teams today. And there we go. I'm done. Thank you very much for having me.
Thanks for being here, Ian.
Very welcome. Am I in time?
It's brilliant.
Perfect.
yeah. I have to say I really enjoyed this talk. I'm looking forward to installing numexpr and bottlenecks, to be honest.
Numexpr is a bit subtle. It only works in some places seamlessly, but bottleneck definitely gives observable results if you're doing numeric operations like means and standard deviations and the rest. That should just give you a win.
I'm going to run some tests.
Will you send a postcard, Vlad? That's the real question.
Absolutely, I think we should.
I would love postcards. I get postcards from all around the world, sometimes from someone's home city, sometimes when they're on holiday up a mountain. I don't care when I get the postcard, I just want to receive the postcard. They make me happy. They remind me that 8 years of contributing to the open source ecosystem and giving talks like this is beneficial and helps people. So it makes me smile, it makes me happy. Please send me a postcard.
All right, sounds like a plan. Yeah, I also liked the part that you're coding in assumptions at research time. right? And then you'll have that to double check your
That's
data.
that's been learned. It's the hard one, one of those hard lessons where I try not to get myself fired from my client engagements, and learning the hard way that the data is always trying to get me fired means that I have to encode those assumptions to try to stop the data getting me fired and stop me embarrassing myself. And so encoding my assumptions is just part of my normal practice. I always teach that when I'm coaching.
One question, do you regularly use asserts or use something like, well, a more dedicated library, like, for example, Great Expectations?
So I don't use Great Expectations. I use Bulwark typically, which will do type checking on Pandas. Great Expectations is another very good library, of course. Normally, for some of the research assumptions, I use asserts because they're quick and dirty. I can just bash them out and just make sure things are happy. Some columns are always greater than 10 and some things have got a certain standard deviation in a range. Just some simple things. Once I'm happy with my code, then I begin to encode up those assumptions better, and particularly for data ingestion. And that's where I use Bulwark. But Bulwark, Great Expectations, or writing some custom code and raising exceptions, they're all super sensible options. The act of putting in some assumption checking is the important bit.
I totally agree. And one also, since we're at this point, what do you usually check for? Do you only check for, let's say, the results of operations when, I don't know, as you've converted the price from int64 to int32, or do you also check some more subtle things like, for example, standard deviation or the curves, the min and max values, stuff like that?
So if I've got names, I want to check that the names have always got more than 5 characters in them. And that the names are less than 10,000 characters where someone has uploaded a document by mistake into the name field. There's a bunch of those kind of silly things, but also does every year in a GroupBy have at least 10 items in it to make sure that I haven't got some data that systemically underestimates the number of activities per time period or per customer grouping or whatever it is. Really, it's anything. I try to think of all the different ways where if a customer says, yeah, Ian, you do know that like 3 years ago we had that data entry error and those results are meaningless. And then, does your machine learning model take account of that? I go, what happened 3 years ago? I didn't see that. That's why I've learned to draw diagrams and then check for anything that looks a bit weird and encode some assumptions there. Because if I go back to the customer and say, look, 3 years ago, something weird happened in your data. It looks like someone just deleted a lot of it. They go, oh, yeah, you found that. That's brilliant. You're speaking my language. You understand me. I trust you. And that helps me build my client trust for those kind of problems. And for me, it's all about building client trust. It's not about the latest, greatest machine learning and the best possible Kaggle score. It's much more about, do you actually trust me to make a business decision on your behalf? And if you don't, because I don't understand your data, this is all not going to work anyway. And as I mentioned in our chat earlier on, for me, it's much more about how do I get value out of a system to get to a deployment to actually make business change occur? And how do I help a team do that better? And so a lot more of my process over 20 years has gone from cutting edge craziness to how do I just do the boring stuff fast and reliably and keep my life interesting at the same time? Like numpy-groupies, I've been meaning to try that for ages. There's hardly any contributors. I want to make that library a little bit better because it's really nice. It solves one specific problem better, and that's great. But it's not the greatest Kaggle result predictor or anything. It's just a boring GroupBy. But hey, it turns out reporting often goes slow. If we can make our GroupBys go faster, so our reporting goes faster, the client's happier. That's it. Everyone's happy. We get to go to the pub sooner, and that makes me happy.
So numpy-groupies for the win.
Yeah, I think that's it. I only tried it a few days ago specifically to talk about this week, and I'm really happy with the results that I get there. And there's no one contributing it, so it's it's under. No one knows about it, so I'm trying to publicize it.
No, it looks really cool. I'll also it's on the to-do list. I also wanted to ask. We have a question in the live event Q&A. Apart from TimeIt, is there any profiler or benchmarks that you would recommend? And they thank you for the presentation, by the way.
It's almost as if you're asking questions that I've written a book about. So yes, absolutely, there's a bunch of libraries, and I teach them both in my book, the High Performance Python book, and the High Performance Python class. Oh, I've got a High Performance class running in 5 weeks' time on Zoom. If anyone's interested, details are on my blog, and ask me questions on Teams. The libraries I teach there are, what do I cover? So C profile built into Python, visualized with SnakeViz to make for a nice interactive visualization, because C profiles output is boring, SnakeViz makes it visual. Really, I use Line Profiler. This gives me line-by-line profiling on my numeric code. I've been using Line Profiler for 10, 15 years. It's brilliant. It just does that job really, really well. When I want to understand why memory goes weird, there's an equivalent memory profiler, and Pandas does some really weird things with using too much RAM sometimes, and memory profiler helps you understand that. And there's a new tool called Scalene, S-C-A-L-E-N-E, which only runs on Linux and Mac, not on Windows yet, which is a better combined CPU and memory profiler for Python code. It tells you per line how much RAM or how much CPU was used on a script. So that's really nice as well. So those are the main profiling tools that I teach, along with %timeit, %timeit, %memit for the memory equivalent. Yeah, I think those are the main ones that I teach. Certainly Line Profiler that's just the tool. Without Line Profiler, I'd cry. With it, my life's pretty easy.
Well, thank you very much. I've made some notes. I have a list of links to check later on. Well, thanks so much, Ian. It's been a great talk. I've had a lot of fun. I really look forward to meeting with you in person once. Absolutely. This whole situation.
Beer as well. I want to raise beers in the real world again.
Yeah, exactly. Or Mai Tais in my case, but
sure, whatever. Or coffees or cakes. And everyone on the call, remember to go and thank your open source contributors. Offer to buy them a slice of cake and a coffee or a beer or whatever. Go and say thank you to them. It makes the world a better place. And yes, I just look forward to us being able to be social in person again.